Hello everyone, I am Tahira Mazumdar, Assistant Professor from IT Department in Ajay Kumar Garg Engineering College. Today I'll be talking on the topic RSA crypto system, which is an algorithm that comes under asymmetric key cryptography. It basically is under the subject cryptography and network security with subject code KCS 074 under AKGEC University. Okay, to start with, this is just a brief outline on the topics on which I'll be talking about. First, I'll give a brief introduction about this asymmetric key cryptography, what exactly it is, how is it different from symmetric key cryptography, and how does RSA work, which is a type of asymmetric key cryptography. Then I'll be giving an example which works on RSA crypto system, and then I'll be talking about the security issues related to RSA crypto system. Okay. To start with, let us first talk about what exactly is RSA, what exactly is public key cryptography or asymmetric key cryptography. Okay, fine. So let us first say that in case of asymmetric key cryptography, we don't have one key, rather we use two sets of keys. Means every unit which participates in the data transmission or communication uses two sets of key. One key is called as the public key and the other key is called as the private key. Now, the public key is a key which will be known by everybody in the network, and this key can be used for the purpose of encryption of messages as well as for the purpose of digital signatures. Now, when it comes to private key, again, as I said, every unit in the network will be having whoever wants to communicate via the asymmetric key cryptography system has to have two sets of keys. One is the public key and the other one is the private key. So in case of private key, that key is known only to that particular unit, whosoever's key it is. And it is the use of private key, it is used to decrypt messages and also to sign signatures when it comes to digital signatures. So public key and private key are two sets of keys which every unit need to have, whoever wants to communicate via in the network and uses asymmetric key cryptography. And the characteristics about this two key is that public key is known to everyone in the network and private key is known only to that particular unit, and we choose the keys in such a way that the key which is private is not at all possible to be known by others in the network. It will be totally private, and it is impossible to determine the private key from the public key. This is not possible. Now, why do we call it asymmetric? We call it asymmetric because whoever encrypts the messages or verifies the signatures cannot do the vice versa or cannot decrypt the message or create the signatures, and hence we call it as asymmetric. Okay, now moving on further on this. So we have, as I told you, in case of asymmetric key cryptography, we use two separate keys. One is called the private key and the other one is the public key. Public key available to everyone in the network, whoever is there in the network, whoever can see that particular node can access the public key of that particular node, and private key is only private to that particular node. Now let us talk about this example. If we look at this example, let us say we have got two people who wants to communicate securely over the network. Let us name them as Alice and the other one's name is Bob. So in this case, if you look at it, Alice, Alice will have her own private key as well as her own public key. Similarly, Bob will also have his own private key, let us name it as like this, PRB, and his own public key. So Alice and Bob will have their own set of private key and public key. Now the logic when it comes to asymmetric key encryption, the logic is that public keys are visible to everyone in the network. Private keys are only private to that particular element, to that particular node. Now, when it comes to Alice, the public key of Alice is accessible to everyone in the network. The public key of Bob is accessible to everyone in the network, and the private key is not so. Now, what the logic is, what do we do so for in the case of encryption and decryption? What we do is that when you want to encrypt a message, for example, we want to encrypt a message, for example, we want to run an encryption algorithm, that is, we have a message which Alice wants to send to Bob. So what Alice does is that Alice encrypts the message using Bob's public key. Now, the point is there's one point which we need to remember is that if we are using anyone's public key, let us say we are using the public key of X for encryption, we need to ensure that we are using the private key of X for decryption. That means we have to go in pair. Whenever we are, be it for the purpose of encryption or be it for the purpose of digital signatures, because digital signature is also another topic which uses this concept of public key and private key pairs. So, the point which needs to be underlined is that whenever we are using a particular element, let us say public key of X, we need to ensure that we are using the private key of X, or if you're using the private key of X, we need to ensure that we are using the public key of X. That means we have to go in pair. Like, it cannot be like this, that we are using the public key of X and we are using the private key of, let us say, A. This is not possible. It should be for the same unit. So, what by this logic, what you're doing is that now when Alice has a message which Alice wants to send over the network. So, Alice has to run an encryption algorithm. Now, we are calling that algorithm as E, for example. This is the encryption algorithm which Alice will be running. Now, this is the encryption algorithm. Now, what Alice does is that, now the question is to encrypt which key to be used, because now from Alice's point of view, what are the keys which Alice can access? Alice has her own private key which Alice can read. Alice has her own public key which Alice can read. And what else is accessible to Alice? For Alice, all other nodes or all other people who are in the network, she can access. Let us say we have the case of, let us take an example, we have talked about Bob. Let us say this is the private key of Bob and this is the public key of Bob. Now, from Alice's point of view, Alice knows her own private key, Alice knows her own public key, and Alice knows the public key of Bob and nothing else. Why Bob? Because right now Alice is trying to communicate with Bob. Had it been with Eve, in that case it would be the public key of Eve. So, Alice wants to communicate with Bob, and to do so, these are the keys which are known to Alice right now. Now, for this, out of this set of keys, which one will Alice use for the purpose of encryption? Whether to use the private key of Alice, whether to use the public key of Alice, and whether to use the public key of Bob. Now, for example, if Alice uses the private key of Alice for encryption, if Alice uses the private key, let us say encrypting a message, if Alice uses the private key of Alice, so in that case, whatever the message is, finally at the receiver's end, to decrypt it, Bob has to use the corresponding pair. If private key of Alice, the corresponding pair is what? The public key of Alice. It should be of the same. If it is Alice private key used, then it should be the public key of Alice only. And Bob has to. So, if Alice is encrypting the message with the private key of Alice, so for decryption, the public key of Alice is required. Now, is this possible? Yes, very much possible. Why? Because for decryption, the public key is required and public key is accessible to everyone in the network. So, it can very well be decrypted. Now, the point is whether it is ensuring security. Now, because this is a public key and if it is public, everyone knows in the network about this public key. So, this decryption can be done not only by Bob, but by everyone in the network. In that case, we'll say it is no more secure. So, that means this combination of using the private key of Alice is not possible. Fine, this is not possible. So, we are right now ruling out the chance of using the private key of Alice. Next is what to do then. Next, what key to use? The next option is, if we are using the public key of Alice for encryption, if the public key of Alice is used, then in the decryption part, we will be needing the public key of, if the public key of Alice is used in the decryption part, excuse me a moment. So, in the decryption part, we will be needing the private key of Alice. Now, whether it is possible for Bob, this is at Alice ends, this is at the end of Alice, and this is at the end of Bob. Now, whether it is possible for Bob to decrypt it using the private key of Alice, the answer is no. Why? Because private key of Alice cannot be known by Bob. It is known only by Alice. So this combination of trying to decrypt using the public key of Alice, this is also not possible. So we are ruling out that combination also of using the public key, or rather using the public key of Alice. Now we are left with which option? We are left with the option of trying to find out whether we can do the encryption using the public key of Bob. So at Alice end, at the end of Alice, we are trying to encrypt the message M. We are trying to encrypt the message M using the public key of Bob, which Alice has. So if you are using the public key of Bob, then the message which is being transmitted, the encrypted message which is being transmitted and received by Bob, to decrypt it, Bob has to use the corresponding pair. So if encryption, the public key of Bob is used, so in decryption, the private key of Bob needs to be used. Now, whether it is possible? Yes, very much possible. Why? The private key of Bob is known only to Bob and to no one else. So, first of all, whether it is feasible? Yes, it is feasible. Next, whether it is secured? Yes, very much secured. Why so? Because this particular message which is being encrypted using the public key of Bob needs to be decrypted using the private key of Bob, and who can decrypt? Only and only Bob can decrypt this message. Nobody else can decrypt or read the message. So the message is totally secured because only the intended recipient can decrypt the message. So this is the underlying concept when it comes to cryptography, when it comes to ensuring security using public key encryption methodology. The encryption is done using the public key of the receiver and the decryption is done using the private key of the receiver. Then we are ensuring security as well. Fine. So this is which was specified here. If you just remember, if you just look back to the previous slide which we said, when the public key is used for encryption, and so public key of whom? The public key is of the receiver is used for encryption, and for decryption the private key is used. Again, whom? Of the receiver. And that's a different concept is used for in the case of digital signature, which I'll take it maybe in some other classes. So this is the main logic. So we can say when it comes to encryption, whose public key is used? Bob's public key is used to lock it. And when it comes to decryption, the private key is used. Whose private key? Bob's private key is used. And I already explained right now why are we using this combination out of the all possible 3 combinations which we have. Now, so this is just a brief summarization of whatever I told right now. We have this public key cryptography. Like when you are talking about Bob, what are the keys which Bob has? We are talking about Bob. So Bob has all the public key. Bob has access to public keys of all who are there in the network, maybe Joe, Mike, Alice, whoever is there in the network. Bob can access the public key of those people as well as Alice's public key. It also has this public key. So Bob, basically what I'm trying to say is that Bob maintains a public key ring where he keeps all the public key of all the people who are there in the network. Right now, for example, Bob wants to communicate with Alice. So from that key ring, Bob will take out Alice's public key. And once it takes out the Alice public key, as I told you in the previous slide, Bob will use the sender uses the public key of the receiver to decrypt the message, encrypt the message. To encrypt the message, the sender is using the public key of the receiver. The receiver here is Alice, unlike the example which I took, and the sender here is Bob, and X is the message which needs to be encrypted, and Y is the ciphertext or the encrypted message that is being created, and Y is sent over the network. Now at the receiver's end, during decryption, the corresponding pair will be used. So since during encryption the public key of A is used, in decryption the corresponding pair, that is the private key of A or Alice, will be used. On the ciphertext is Y, will be used. So this is the decryption, and we'll get back the original message which was used. So here, if you see, in case of Alice, the public key of Alice is used for encryption, and for decryption the private key of Alice is used. So this ensures nobody else can decrypt the message. It will be only Alice who can decrypt the message. Why so? Because why nobody else can decrypt the message? Because the private key of Alice is known only to Alice and no one else. And so by this method we are ensuring that the message which we are transmitting is totally being secure. So this is a brief idea about the asymmetric cryptography. As I told, we have Alice, we have Bob, we have the encryption method, where we have the plain text which needs to be encrypted to the ciphertext, and to encrypt the message we are using a public key. Out of all the public keys that are available in the network, we'll be using the public key of the receiver whom we want to send. Public key of the receiver. This over the network, what will be transmitted? The ciphertext will be transmitted. At the receiver's end, the ciphertext will be taken, it will be decrypted, and here what will be used? The private key of the receiver. The private key of the receiver is used at the receiver's end, and in encryption, the public key of the receiver is being used. Now, so we have this important methodology, we have this important points that needs to be kept in mind right now. So we need to know what is the, now if you look at the whole scenario in totality, what are the important things that are needed for this algorithm to run? The first point is we need to know the keys. What are the keys? The public key, private key of Alice, the public key, private key of Bob. Only when we know the keys, then only we can do the encryption or decryption. So first point is we need to have a procedure to generate the keys. This algorithm needs to be executed in case of encryption, because we need the keys of Bob. Why? Because we need the public key of Bob for encryption, and we need the private key of Bob for decryption. So the key generation procedure needs to be executed at the receiver's end. Thereby, the keys, the public keys of Bob and the private keys of Bob can be generated. Once the keys are generated, then we can follow with the process which we need to do. For the very reason why we are doing this, it is encryption at the sender's end, where the public key of Bob will be used. And decryption at the receiver's end, where the private key of Bob will be used. So we can say in case of asymmetric key crypto system, we have some important 3 steps. The first step is to generate the keys, the public key and the private key. After the generation keys is done, that means how to generate the key, we need to know how to generate the key. Next, once the keys are generated, we need to know how to encrypt the message, and finally we need to know how to decrypt the message. So this we have 3 important steps that needs to be stated when it comes to following asymmetric key cryptography, or rather we can say we need to have 3 important algorithms, one for key generation, one for encryption, and the other one for decryption. And I'll be taking up each of them one by one. So under asymmetric key cryptography, there may be various algorithms. In this particular example, or in this my particular lecture, I'll be talking of an algorithm which is called RSA. RSA is an algorithm where we will have steps for how to generate the keys, how to decrypt the message, and how to encrypt the message. So this is a brief summarization of public key crypto system. We start with a message M. We do the encryption of a message. To do the encryption of a message, we take the receiver's key, we use the receiver's private key for encryption. After the message is encrypted, we get a message Y, and once this message Y is transmitted over the network, what we do is this is like, if you don't want something, if you just want security, then we can rule out this one. Otherwise, this is an extra point which is there. Right now, I'm not talking on this. Okay. So when it comes to here, in this case, we treat, unlike in symmetric key cryptography, the plain text and the ciphertext are treated. Okay, just give me a moment. So where यहाँ पे थोड़ा स्टॉप करना है, मैं दोबारा स्टार्ट करूँ, दोबारा स्टार्ट कर रही हूँ, हाँ. Now, so here, unlike in this case of symmetric key cryptography, the plain text and ciphertext are treated as integers. In case of asymmetric key cryptography, because in symmetric key cryptography we have different approaches where it's not required that we need to take them as integers. We can take them as strings. We can take them as characters as well. So if you just summarize the encryption and decryption algorithm, so in the encryption part, we are using the public key of the receiver, and in the decryption part, we are using the private key of the receiver. In the encryption part, on the plain text, from the encryption algorithm, the F here is your encryption algorithm. We get the ciphertext at the sender's end. The G here is your decryption algorithm. we apply the decryption algorithm on the ciphertext and we get the plain text. This is a brief summarization of the encryption and decryption algorithm. Now, if you just compare symmetric with asymmetric key cryptography, symmetric cryptography, basically we can't just rule one of them, we can't rule out one because of the other. Both of them basically exist in parallel and are equally important. In fact, we can say symmetric key and asymmetric key cryptography, they complement each other. In such a way, we can say the advantage of one can be compensated by the disadvantage of the other. So, we have this topic of symmetric key cryptography where, unlike this two keys that are used in asymmetric, that is public and private key, in case of symmetric key cryptography, only one key is used, which is known to both the sender and the receiver. So, here I am not talking about symmetric key cryptography in more detail right now, because that's a different lecture again. Maybe I'll talk about it in some of the lectures. But if you want to compare symmetric key cryptography with asymmetric key cryptography, we can say in case of symmetric key cryptography, the conventional encryption is basically referring to the symmetric key cryptography. So, in case of symmetric key cryptography, we use the same algorithm both for encryption as decryption, and we use the same key, which is exactly the vice versa when it comes to public key encryption, or we can also say when it comes to asymmetric key encryption, that is the same thing. Here for encryption we use one algorithm, and for decryption we use a different algorithm, and we don't have the same key, but we have different sets of keys. One is used for encryption and the other one is used for decryption. Here the sender and the receiver, they share the same algorithm and the same key. Here they don't have the same algorithm and the same key, rather the sender and the receiver must each of them have one of the matched pair of keys. As I told you, the keys should be used going in parallel. Like if someone is using the private key of A, for example, at the encryption part, or at the sender's part, just the other pair, that is the public key of A, will be used at the receiver's part. Now, the key here, when it comes to needing the security aspect, the key in case of symmetric one, the key must be kept here. That only single key which is there, that must be kept secret. Here only one of the keys kept secret, which we call it as the private key, and it is practically impossible to decipher a message if no information is available. Here again, same thing we can say, it must be impossible or at least impractical to decipher a message if no other information is available. So, to determine the key, what is required, if for example from an attacker's point of view or from a crypto analyst point of view, you need to have knowledge of the algorithm is required, plus you can have samples of the ciphertext to identify or to make a guess about the key. Now, here in case of public key, what is required? The knowledge of the algorithm plus one of the keys plus samples of the ciphertext they must be insufficient, we can say, to determine the keys. So, we can say both of them are equally important, symmetric and asymmetric key cryptography. One does not eliminate the need of the other one, and we can say they can run in parallel, and one compensates or balances or edges out the disadvantages of the other and vice versa. So, let us start with the next topic, the RSA crypto system, which is an algorithm that uses public key cryptography or asymmetric key cryptography. So, this is an algorithm under asymmetric key cryptography. RSA basically is named after its inventors, where it stands for reversed Shamir and Adleman. So, this RSA comes under the name of the people who have developed this algorithm, and it is basically an algorithm that works on the principles of asymmetric key cryptography. The working procedure of RSA is, we have this 3 steps. As I told you, every encryption algorithm in case of asymmetric key cryptography will have 3 steps. First is the generation of the key, followed by the encryption algorithm, then followed by the decryption algorithm. So, we have these 3 steps, the key generation, the encryption and the decryption algorithm. So, if we have, these are the steps to generate the key. I'll talk about these key steps in detail in the next slide. Once the keys are generated, the public keys will be generated and the private keys will be generated. As per this algorithm, the public key will be ENN and the private key will be D. And this algorithm does the encryption using the key ENN, and this algorithm does the decryption using the key D. Fine. Now, the process is, we'll be talking about how exactly E and N is generated and how exactly D is generated using the key generation part. Once these values are generated, we go for the encryption method followed by the decryption method. So, we are talking about the key generation part, that is this particular part. We are talking about this particular part right now, this particular part. So how exactly do we generate the keys? This is the first step we'll take. After this, we'll come to the encryption, then followed by the decryption. Now, when it comes to generation of the keys, the algorithm which RSA uses is that it selects two large prime numbers, let us say P and Q. They are two very large prime numbers having the characteristics that both of them at any cost should not be equal. Then using these two prime numbers, we calculate the value of n, which is equal to P into Q. Then we calculate the value of phi of n, which is equal to P minus 1 into Q minus 1. We all know how to calculate this. Then what we do, we select a value E which lies between 1 and phi of n, and E is chosen in such a way that it is a co-prime to phi of n, right? And once we have selected the value of E, then we select the value of D. Or rather we can say, we will not say select, we will compute, we select the value of E, and rather in case of D, we compute the value of D. And how is the value of D computed? The value of D is computed by finding out the multiplicative inverse of E modulus of phi of n. What do you mean by multiplicative inverse? It means if we multiply E and D, we get a value of 1 mod of phi of n. So that should be the characteristics. We need to find out the value of D in such a way that when we multiply E and D, we get a 1 once we apply mod of phi of n. Now, so right now, if you look at this, particular stage right now, what are the values we know? We know the value of E, which is a value that we have chosen basically between 1 and phi of n. We know the value of D, which is basically the inverse of E, and we know the value of n, which is basically the multi-product of P and Q. So out of these three values, what we do is that E and n, that means the first two, are selected as the public key of that particular unit, which will be the receiver in the network, fine. And then we select the other one, D, as the private key. So n and E will be the public key and D will be the private key. To whom? To that particular node where this algorithm is being executed. And finally, we return these values of public key and the private key is returned. Okay. So this is how it starts. The value E and N and D has been returned. Now, next is, once the key generation part is completed, next is how exactly encryption is done. Once the key is generated, next we'll learn about how encryption is done, followed by how decryption is done. So let us come to the encryption part. So when it comes to the encryption part, how does RSA encryption work? RSA encryption works on the logic that, as I told you, encryption is done at the sender's unit, and the sender needs what? The public key of the receiver, and the public key, as we have said in the previous slide, the public key is E and N. So E and N of whom? Of the receiver is being used by whom? By the sender. This encryption algorithm is executed at the sender's end, and this key will be used. What is P? P is the plain text which is to be encrypted. So on this, we apply a fast exponentiation method. It is basically an algorithm where we can compute fast, in a very fast way, the exponential values. What does this algorithm do? Or we can also say, instead of fast exponentiation, we can also say we are calculating the value of C as P to the power E mod of N. P is what? P is the plain text, E is the public key, and N is a public key that is shared over the network by the receiver. So after this value of C, and because normally these values are very big, E is very normally, E and D are big. So to do the exponentiation, either you can go for a direct method of calculating, or you can go for an algorithm fast exponentiation, which has a comparatively faster way of calculating the value of P to the power E mod of N. Once this value is calculated, the value of C is returned. So the value of C is returned, and C is now communicated over the network. At the receiver's end, this C will be used for decryption. So at the receiver's end, this C is used for the decryption. If you remember, at the receiver's end, the private key is used. So D is the private key of the receiver, and N is known to all. Fine. So at the receiver's end, the plain text is calculated how? By using the equation C to the power D mod of N. And to do the calculation of this mod of N, to do this calculation, we can do it through normal loop process, or you can go for a method algorithm which is called fast exponentiation. It does the same thing basically. Once this algorithm is completed, we return the value of P. So we return the value of P. So this is how, this is summarization of the entire start. We start with the plain text, do the encryption. In the encryption, we are using the public key of the receiver. Once we do the encryption, we are getting the ciphertext which is transmitted over the network at the senders and the receivers end. The ciphertext is used, and it is using the private key of the receiver to calculate the plain text, and finally the plain text is received by the receiver. So I just explained both the steps now. This is the complexity. So this is if you summarize it, this is a polynomial complexity because C is equal to P to the power E mod of n, the ciphertext, and the plain text also has a polynomial complexity. How? Because we are calculating plain text as in the form of C to the power D mod of n. So for any attacker to find out the plain text, it basically has to find out the root of, because C is equal to P to the power E. So how do you get P? So you need to find out the root of C to root to the power root of Eth root of C mod n, which is having exponential complexity. So we can summarize it by saying that the encryption or the decryption is having polynomial complexity, but the attacker to hack this message and find out the plain text from the ciphertext is having exponential complexity, and so it becomes difficult for others in the network who are not intended for this message to decipher the message. So this is an example of where RSA is used. Let us say B, and we are choosing, we have Bob who chooses 7 and 11 as the two values of two large numbers P and Q. So based on this, it calculates the value of n. What is n? N is the product of 7 and 11. So n is 11 and 77, sorry. And then based on this, the value of phi of n is calculated, where it is equal to n minus 1 minus p into p minus 1, which is equal to 60. So once these two values are calculated, the value of n is calculated, the value of phi n is calculated, then right now Bob is doing all this. So Bob basically is the receiver, because in case of RSA, we need the keys of the receiver. So next, Bob chooses the value of E and D from Z60 star. Now what is E? E is chosen as 13. E should be a value between 1 and phi of n. What is phi of n? Phi of n is 60, so it should be between 1 and 60. So E is choosing 13 in such a way that this is the value of E should be chosen in such a way that it is a co-prime with phi of n, which is 60. Then after that, E is chosen, then Bob has to do the necessary calculation to find out the value of D. D is 37, so D is 37 means E into D. That means what? 13 into 37 will be equal to 1 mod of n, that is mod of 77. So that characteristic should be there. So D value is 37. Once these values are known, next you can go for encryption decryption. Here for example, the plain text 5 is to be sent by Alice to Bob. So Alice will be using the key of Bob, that is why Bob's keys are calculated. So to do the encryption, Alice uses P to the power E. If you remember, E here is 13, so P to the power F5 to the power 13, which is equal to 26. And in terms, when it comes to decryption, it will be the vice versa. We will start with the ciphertext 26 to the power D. D is 37, so 26 to the power 37 after calculation will come out to 5. So this is just an example of how encryption can be done at by using RSA. Encryption and decryption can be done at the senders and the receivers end. These are some of the issues in case of RSA security. These are some of the possible approaches that tends to attacking RSA, like brute force key approach, where brute force means trying out all possible combinations. It is practically infeasible with given size of numbers, because we have already seen we need to have the brute force approach. It has almost exponential complexity, so the time requirement is very high. So it's not possible at all to make a brute force attack. Mathematical attacks like factoring problems, which are based on the difficulty of computing the phi of n, which is also very tough to do so. Timing attacks, which depends on the running time of decryption algorithm, gets also very difficult to be implemented. And we also have this chosen ciphertext possibilities, which are taken care of, like we can say when it comes to chosen ciphertext, RSA to a certain degree is vulnerable to that. Here in that case, attackers can choose ciphertext and gets the decrypted plain text back by using the chosen ciphertext attack. And we can basically, this thing can be used to exploit the property of RSA to provide or to help the cryptanalyst to provide more info about the algorithm. We can counter this with a random pad of plain text or use optimal asymmetric encryption algorithm, which is a little advanced version on this. So these are some of the issues concerning RSA. So I'm winding up for now. This is the reference materials which I have used. I have referred the book by Firozan, Cryptography and Network Security, and by Stallings, Network and Cryptography and Network Security Principles and Practices. That much for now. Thank you.